everyone. Okay, so I just want to tell you maybe a little bit different story than what you heard here today. Some really interesting stuff I already heard, and I'm so happy to hear that things are more moving in towards an ecosystem type model. Just want to see if this works. I'm clicking. There we go. Just say, go it back. Okay. So I'm a biologist, biochemist by training, specifically focusing on the field of computational systems biology. For the last 7 years, we're about a group of 80+ people, mathematicians, biologists, physicists, really bringing together a lot of biomathematical models of human physiology and building one comprehensive model of your physiome, as it's also called by our group. And we've wrapped this with an API for anyone to get easy access to these models. It's important to say what we're not. We're not a machine learning company, we're not an AI company, but we can feed our information streams to these type of companies and other companies as well. But basically what we do is we take biomathematical modeling and we employ that to build a comprehensive digital simulation of your unique physiology. So to showcase this, I want to use an example. We used a guy, Simon is his name, he agreed that I could show his bare chest and his data to you. And his specific case, what we did is we subjected him to some stress. We took him to a sports physiology laboratory, we got him in a sleep center, and we also put one of these devices, a reference device that only has optical sensing and accelerometry around his arm. And we chose that because that's the predominant technology currently being used in the market. And it was very difficult, we had to discipline ourselves, but the key idea was to showcase how powerful this biomathematical modeling is if you just use those few input streams. So just as a start, you will see here that we can, this is 48 hours of his data, and we could, with ease, with this modeling platform, distill things such as stress, exercise, and sleep. And as that may be interesting, I want to show you what we can open up further, specifically also focusing on activity here in the first screen. In this specific screen, you will see we can open up the metabolic activity of an individual with this modeling approach, but not just that, we can open up, for instance, the phosphogenic, your glycolytic, your aerobic system, and we can say what these different systems, how they contribute towards your total energy usage. Furthermore, we can determine very accurately your VO2 max with a 94% accuracy. That's about the same as a submaximal test you will do in a sports physiology lab. We can also even gauge core temperature and skin surface temperature by just using a wearable optical sensor and accelerometry inputs. We've also, because things such as corporate wellness and insurance is quite interesting to us, we started focusing on stress, and if people say they're interested to measure stress, the first thing I asked them is, what is this thing called stress that you are talking about? Because I've realized in these discussions that a lot of people have a lot of different meanings for stress, and we focus, stress for us is very much a physiological definition. We always love to benchmark again against the clinical gold standard, so we chose cortisol levels, in this case salivary cortisol, because it's an easy one to measure, it's not so invasive, and just wanted to show we can not just detect your stress intensity and where these stressor events happen just with these inputs, but we can even to a reasonable degree of accuracy at this stage already predict your salivary cortisol. And that's very, very interesting for corporate wellness applications and also for sports, because in overtraining you get different chronic and acute stress type conditions that you then can track more on a hormonal level. Lastly, I want to show you one of these screens, just a sleep measure. Now, most traditional accelerometer-based sleep measuring technologies can distinguish to some degree between your light and deep sleep, but basically it only uses motion as a proxy and then gauges your different sleep stages. It struggles with things like REM sleep. It struggles to really get accurate descriptions of how your REM and your non-REM sleep relay each other. And we've built a model, a cardiorespiratory model, that could open up these sleep phases with much higher accuracy. All the turquoise color bits that you see in this graph is where we exactly compare with a polysomnograph, a hypnogram from a sleep center. And we've also partnered with a few sleep centers across the world to further build out these models. So the world, I've said we've disciplined ourselves with optical sensing and with accelerometry. I think that's going to change in 2016. We see a lot of interesting different inputs or data streams, from the continuous bits to the periodic, to the episodic and the static. And I'm talking about your genome information, your SNP information, your microbiome information, basic inputs such as weight and body fat estimations from scales, more invasive type measurements. For some reason it seems we've completely lost urinalysis during the last couple of years, which is actually quite useful. But all these things can be fed to a computational systems biology based model. And that really excites me because there's some interesting things you can open up with this. So in this 200 models that we've modeled, we're very much focused on the cardiorespiratory system, little bits of the nervous system. So we've modeled the hypothalamus, pituitary, adrenal axis, and we've also looked more at your body composition model as well. But we're now actively focusing on these different bits of models, starting to look at mathematical models of your gut, looking at digestion, looking at hydration and how hydration is affected by these different components. And we're slowly starting to engage with partners to feed these different streams, continuous, periodic, episodic, and static data streams into this model system. And it's really to open up measurements that are currently inaccessible, difficult to get, costly, invasive, but also to derive mechanistic understanding. Just like your genome, your physiological model has a ton of parameters in them that makes it personalized for you as an individual. And this really opens up personalized medicine. Every one of us has a unique vector of parameters that we can then track in time. We can see how with different clinical conditions, with different lifestyle changes, how these parameters change and deviate over time. And where things become really interesting is where this more analog world and then the genomic or the digital world meet, where we can see for specific genome profiles with specific SNP profiles, for instance, you can see different trajectories in these long-term parameters. Then also to derive context and more, as I mentioned, these longer-term trajectories. So one that I just want to give you a sneak peek of, by just going beyond the optical sensor and the accelerometry bit, by just employing a weight scale, something like the Withings or the Fitbit scale, we could do something to this extent with our modeling. Admittedly not wrapped in our API yet, still refining, but this will be made available to all our partners very soon. And by the way, we're biochemists, we're not musicians, so we cannot track real-time energy intake just yet, but we can do a 24-hour retrospective energy intake with reasonable amount of accuracy. We're plus minus a banana accurate at this stage. And as you can see, tracking the weight, we can follow your energy intake that we estimate and compare it to real-time measurement, and you will see there's quite a good trajectory following there. So brings me to the last point. Like I started off, I said I'm very excited to see that we are heading into this ecosystem space. And I think living systems, if I ask myself which systems have really managed to build robust ecosystems, robust networks, but these robust networks are still able to react upon change in the environment, they're able to evolve, they're able to be more fluid, and that is actually living systems. So we can go back to biology and ask ourselves, how do we need to design these ecosystems around our own complementary bits of expertise? So that is a core part of what LifeQ is also venturing in with a lot of different partners that you will know of, people like Analog Devices, Texas Instruments, even from the semiconductor side, all the way to some really large insurers that you will see some announcements this year. And it's to bring all these different bits together. People have different expertise in devices, in data visualization, in services, really taking this information and then presenting it in a digestible way or in a presentable way to users or insurance, corporate wellness, other stakeholders, and even things such as recommendation engines, machine learning partners, semiconductor partners, for instance. At last CES, I said something to the extent that data is the new Lego. Just like material science in the last decade came up with interesting composites, interesting materials, we would never have been able to fathom that there would be something like a mobile phone that I can have in my hand that can take my audio signals, again, transmit that, change those signals, transmit it in a way to another bit of material somewhere out there in space, and I can then again receive the call on the other end of the world. Just like this paradigm, just like we could not fathom that, we are yet to fathom how data will be recombined. Data is the new Lego, and we're going to recombine it in very, very interesting ways. So now we've made available a bunch of Legos for partners to play with. The nice, really cool thing with about computational systems biology and this type of modeling is 1 or 2 new inputs open up 10, 20 more outputs on the other end for partners to use. So we really see an explosion of Legos in the year to come. And with that, I want to thank you. I wanted to keep it short and sweet and allow for some questions.